Nima Aghniaey from University of Ottawa, who's going to talk to us about testing steel fiber reinforced concrete under reverse cycle loading. Nima?
Well, hello everyone. My name is Nima Aghniaey. I'm a master's student at the University of Ottawa, and today I'll be talking about my experimental project, the behavior of steel fiber reinforced concrete beams under reverse cycle loading. First, I'm going to give you a little background information, and then we're going to move to the use of steel fibers in beams, and then we're going to talk about my experimental program, and then we're going to discuss the results and into some conclusions. Steel fiber reinforced concrete, it's been around like for about 20 years now, and it's basically a composite material composed of regular Portland cement concrete and short discrete steel fibers. As you can see there, they come in different types and shapes. They can be different. They can have different cross sections and different length or geometry. The benefits of SFRC has been shown in several past research studies. It's been shown to increase the post-peak ductility, also the energy dissipation capacity, improves the fracture toughness, and also improves the crack control and the damage tolerance of structural elements. It also improves the confinement of structural members. There's fibers have the ability to basically bridge cracks, which are basically preventing the cracks from opening up, which increases the tensile strength of concrete, and also it has a potential for replacing traditional transverse reinforcement in concrete structures. The objective of my research program was to study the effects of steel fibers in beams in reverse cyclic loading, and also to examine the potential of steel fibers to replace transverse reinforcement. As in most experimental research programs, we had to prepare the beams at the testing specimens. So we started with the beam design. We built the formwork, the reinforcement cages. We did the casting in the structural lab at the University of Ottawa. Then we did the instrumentation for measurement device for measurement, and also loading setup, and then we started testing after. You can see my formworks and cages in the bottom there, and the mixer that I used for preparing the beams. SFRC and SCC. Well, SCC, as you probably know, is self-consolidating concrete, and SFRC is just normal concrete with steel fibers added to it. But the problem with SFRC alone is that when you add steel fibers at higher contents, it loses its workability. So it's hard to work with in most structural applications, which require around like 1 to 1.5% steel fibers. To solve this problem, we combined the SCC with steel fibers, which gave us a more workable mix, and had a bunch of benefits, and was very workable. You could use it in a lot of different structural applications, and you needed a lot less vibration, basically. You can see that's a slump flow test, which is usually conducted to measure the workability of the SCC, and that's when we're doing the SCC mixes. So as I mentioned, the slump flow test is used to quantify the workability of SCC mixes. You basically measure the spread of the diameter of the spread, and for normal SCC with no steel fibers, the diameter of the spread is about 600 millimeters. When you add steel fibers, it reduces to about 400 to 500 millimeters, depending on the amount of fibers. At 0.5%, it's very workable, no vibration required. At 1%, it is still workable, minor vibration may be required. And at 1.5%, it loses a little bit of workability, and you will need vibration during casting. We used the King MS SCC concrete mix, which came in 30 kilogram bags. It's pre-mixed, so it's pretty easy to work with. We basically add water to it and cast the beams. Here are some details of the mix. We use hooked end steel fibers, Dramix ZP305 type. Tensile strength is pretty high. It's 1,345 MPa. The length of 30 millimeters, diameter of 0.55 millimeters, which gave us a aspect ratio of 55. It also came in packages of 20 kilograms. We did some material testing. Basically, we did 81 standard size concrete cylinder tests. We also got some full specification diagrams for the concrete tests. You can see in that table the compressive strength of for the concrete used in all of my specimens, and also this specification diagram. And you can see the improvement in the post-peak behavior of the SFRC. The most improvements in concrete with 1.5% steel fibers. We did some, before starting my main experimental program, we did some preliminary investigation. We tested 6 beams with different steel fiber contents and different fiber types. We used hooked end and straight steel fibers, and also 0% to 1.5% fiber contents. It was a cyclic loading test, so it was loading and bending, basically, loading and bending in one direction only. And here is, you can see the cyclic load displacement curves there. We observed a huge, significant improvement in the shear capacity of the beams because of the steel fibers. There was we saw an improved energy dissipation capacity of all beams reinforcing steel fibers, improved ductility, improved damage tolerance and crack control, and also more ductile behavior. And my main experimental program consists of constructing 9 beams with different steel fiber contents, varying from 0% to 1.5%. We constructed 2 control specimens with 0% fiber with identical longitudinal reinforcement. We also used various boom spacings, varying from D to D over 4, where D was the effective depth of our section, around 204 millimeters. This was to investigate the effects of boom spacing on the properties of the structural section as well as the effect of the steel fibers. Again, as I mentioned before, we used King MS-SCC mix and the Dramix ZP305 hooked end steel fibers. We only used one type of steel fibers in all of our beams. And all of the beams were designed to conform to CSA 820.3 clause 21.22, which basically states that the positive moment capacity should be at least 50% of the negative moment capacity at the face of the joints. This slide shows my loading setup at the top there. We had the hydraulic jack load beam in reverse cyclic loading, so it was a double valve hydraulic jack. It was fixed, it was like a hinge at the end, but it was fixed with respect to vertical displacement. We placed steel strain gauges in the longitudinal steel reinforcement as well as the hoops. We had displacement cable transducers to measure the rotation of the plastic hinge as well as the rotation due to anchorage slip and the shear deformations. We also measured the vertical deformation. as you can see, my beam base is basically composed of two cantilever beams joined in the middle through a concrete block. Here is this table that shows the details of all of my specimens. You can see our consensus transfers, also spacing, span depth, ratio of 5.4, and all other details. As far as the results, we obtained a lot of data from tests, including misspan deflections, the applied load, which was measured by means of load cell, longitudinal and transverse steel strains. We measure shear deformations, plastic rotations, crack width, and also we assess the level of damage to our specimens by visual inspection. And the first step, we did the load force displacement first, and by doing that, we tried to see, basically compare the improvements resulting from the application of steel fibers. As you can see, there's those are the force displacement diagram areas, basically areas enclosed by force displacement diagrams for my P/2 series, and we observed that the energy dissipation capacity for beams with higher steel fiber contents increases. As you can clearly see the diagram, these are for diagrams for my other beams. In these diagrams, the hoop spacings are the same, and we are only increasing the fiber content. As you can see, the area under this diagram, which is my P/3 beam with 1.51% fiber, is a lot larger than my P/3 beam with 1% fiber, so 1.5%. And again, in that diagram, you can see the improvement in energy dissipation capacity of the beams. The only exception to that was my P/2 1% specimen, which has a slightly lower energy dissipation capacity compared to the specimen with 75% fiber. These are the hysteresis curves, or load displacement curves for all of my beams. At the top rectangle there, you can see my P/2 series with 0 to 1.5% fibers. If you look at the post-beat ductilities, in the negative region, you can see a significant improvement in that area. In the positive region, we also had a little bit of improvement, but our number 15 reinforcement ruptured at an early stage, and that's why you're getting that unsymmetrical shape in our hysteresis models. So we have different amounts of longitudinal reinforcement, positive and negative reflecting. My P/3 series again showed significant improvement, also some strain hardening effect there. As well, in P/4 series, we also observed significant improvement in post-beat ductility, and some strain hardening effect there. Flexural strength of the beams were also improved by addition of steel fibers, as you can see here. Comparing the SFRC beams with the control specimen, we can see improvements in all beams except P/2 1% beam, which seems to be my specimen with problems a little bit. But in all the other beams, especially P/3 1.5%, we had a huge 1.5%, 5%. All of our beams, failed deflection as we expected it to. So the span to depth ratio was designed such that the shear strengths would not be that significant, so our beams would fail in flexure. There has been a lot of research several researchers in investigating the effect of steel fibers on shear strength of beams, but we haven't seen a lot of research in studying the effects of steel fibers on flexural behavior of concrete. That's why we try to have our beams fail in flexure. As far as damage control, you can see this is my D/2 series, so they all basically have the same roof spacings and different fiber contents. As you can see, as the fiber content increases, we see less stalling, less material loss, and smaller cracks. This is the 1.5% D/2, 1.5% specimen compared to D/2, 0%. You can almost see here that this is D/3 and D/4 series. Again, the same effect was observed. And I'll do the 1.5% fiber, which was just the one even in that series. So in all specimens, we observed improved confinement and cover response. We observed improved damage tolerance, which basically meant less spalling and concrete degradation, as we saw in the pictures. And we saw increased toughness, which resulted in delayed crushing out the concrete. So we would have a more ductile response from the beam. And also the buckling